We're investigating the effects of viscosity on a rotating fluid, specifically the consequences of viscosity breaking the leading dynamical balance, geostrophy. This typically occurs at the top and bottom boundaries of the fluid and is the primary mechanism for getting momentum into a rotating fluid. We will start by picturing a uniform geostrophic flow of velocity u0 in the x direction. It is in geostrophic balance, so the Coriolis acceleration arising from its flow, 2 omega u0, is balanced by the pressure gradient in the y direction, perpendicular to the flow. The geostrophic equations that describe the force balances are 2 omega u0 is equal to negative 1 on rho dp by dy, and given that the flow in the y direction is 0, geostrophy requires that the pressure gradient in the x direction is 0. Near to a horizontal boundary, viscous stresses penetrate some vertical distance delta into the fluid, reducing the velocity in this viscous boundary layer and thus reducing the Coriolis acceleration here, rendering this reduced acceleration unable to balance the across-flow pressure gradient. This initiates a flow in the y direction. That is, near to the boundary, the flow begins to rotate with height. We are now going to go through the derivation of equations to describe the flow within this viscous boundary layer. We begin with the steady, rotating momentum equations, but this time we hang on to the viscous terms. So these are the geostrophic equations in x and y with viscosity, and the hydrostatic equation in the vertical. We want to solve these equations given the boundary conditions that u equals v equals 0 at z equals 0, the boundary, and that as z gets large, u goes to u0 and v goes to 0. Now the hydrostatic equation implies that the interior pressure gradient also applies in the viscous boundary layer, allowing us to relate the interior geostrophic balance equations to the boundary layer equations. This removes the pressure gradient in the x direction, giving 2 omega v as equal to the x viscosity term. It also allows us to substitute 2 omega u0 for the pressure gradient in the y direction, giving 2 omega times the difference between the velocity in the interior and the boundary layer as equal to the y viscosity term. These two equations are second order, and as they stand, we don't have enough boundary conditions to solve for u or v. We can progress, however, by introducing the complex variable I. Note that this is just a mathematical tool, and that the flow associated with the complex variable is not actually imaginary. That is, if the flow is indeed able to be modeled by these equations, we should be able to perform whatever mathematical tricks we like to examine the flow in different ways. So, we multiply the second equation by I and combine. This reduces to give 2I omega outside of u plus IV minus u0 minus the viscosity times the second vertical gradient of u plus IV is equal to 0. Next, we define big Z as equal to u plus IV on u0, and we substitute this big Z back into the combined equation, giving us viscosity times the second vertical derivative of big Z minus 2I omega outside of big Z minus 1 equals 0. This is now a second order equation in big Z. We want to solve for big Z with the boundary conditions of u and v at little z equals to 0 and little z goes to infinity. The solution is big Z equals 1 minus the exponential of the square root of 2I omega on viscosity times little z. This solution has both real and imaginary parts, which can be separated and rearranged for u and v, where we have made the substitution for delta as the square root of viscosity on omega. These equations describe the flow within the viscous boundary layer, which has a thickness scale of delta. The flow described by these equations is referred to as the Ekman spiral, and it's the result of viscosity in a geostrophic flow. This viscous boundary layer is known as the Ekman layer, and it's named for Vagen Walfrid Ekman, a Swedish oceanographer who, as an undergraduate student, proposed this theory to explain the observed drifts of icebergs in the Arctic Ocean. We can plot these solutions and get an idea of the shape of the flow in the Ekman layer. Velocity in the along flow direction goes from 0 up to u0. Velocity in the across flow direction goes from 0 to some maximum at an intermediate depth just below 1 delta before dropping back to 0. Plotting these two together gives a distinctive spiral, which is known as the Ekman spiral, as you traverse from the boundary vertically through the Ekman layer. Note that immediately adjacent to the boundary, the flow is at 45 degrees to the interior flow, and that integrating the velocities through the layer actually gives you a transport that is normal to the free stream direction. We can see this effect with the lab demonstration. Here, the tank is at solid body rotation with the ducts and particles on the surface acting as passive traces. The purple dye is being emitted from crystals on the bottom within the Ekman layer. Speeding up the rotation of the tank results in an outward transport within the Ekman layer that's oriented at 45 degrees to the radius outwards. Decreasing the tank rotation, so spinning down the water, redirects the transport in the Ekman layer inwards at 45 degrees to the radius.